In this video, we are going to look at angles of elevation and depression, understand what they mean, and then how we can use them to solve trig problems. Imagine that you have a really tall building in the city and you wanted to run a Y cable that ran from the very top corner of this building all the way down to the ground so you could have a bit of a flying fox going. Now you can start to see that it's showing us a bit of an angle, a bit of a triangle. Now there are a few angles that we can see in this diagram. So this dotted line, it's an imaginary line that's just helping us look at this situation. So we can see that there's one triangle over here. And if you look very carefully, there's actually another triangle over here too. So in terms of angles of elevation and depression, if we're at the top of this building, this point right here, the angle that the top of the building makes with the cable, so the horizontal line, the dotted line, and then the cable, we call this one an angle of depression. So depression is another word that means to go down. So this angle starts from the horizontal and it goes down towards this Y cable. Now, if we're at the bottom of this Y cable at the end of the flying fox, we've also got another horizontal line. There is another angle at the bottom down here. So this angle is made using the horizontal line and it goes up to meet the cable. This one we call the angle of elevation. So elevation meaning to go up. So angle of depression just means that this is the angle that is made with the horizontal line going down. Angle of elevation, the bottom horizontal line going up. So we can use these terms and these types of diagrams to help us solve a series of different problems. Let's just have a look at a couple of different situations where there are angles of depression and elevation before we start tackling these. So here we have a skydiver that's mid-air, and then down at the bottom on the ground we have a position, so this is marked with the X, that the skydiver was actually aiming to land. So what we can do is let's go from the dead center of the skydiver, let's draw a diagonal line down to the landing spot, and then let's draw a horizontal dotted line to represent how far away horizontally the skydiver is. You could even do a dotted line going down to show how far away the skydiver is vertically as well. And we can do the same on the other side. So if you're the skydiver looking down to the landing position, you would be making an angle of depression because you would start off looking straight across the horizon and then tilting your head down, making this angle. So this again is an angle of depression. Now, if you were down on the ground at the landing position and you had to look up towards the skydiver, you'd be looking up at an angle of elevation. Now, the interesting thing about these two angles, so the angle of depression and the angle of elevation, is that they are both equal. So remember also that these would make right angle triangles here and another right angle triangle there. So you can use this information to help you solve different problems. So let's imagine that this skydiver is 10 meters up in the air and horizontally the skydiver is 12 meters away from the landing point. So we've got two sides labeled in our right angle triangle. Let's find the angle of elevation. So now we can use our existing trig skills to solve a problem like this. Our first step would be to label the sides. So looking from this angle down here, the opposite angle is 10 meters. So let's label this one as opposite. Then we also have an angle that's directly next to, so we label this one as adjacent. Now we need to think which ratio would we use that involves opposite and adjacent. So the perfect ratio for this situation is the tangent ratio. So tan theta equals opposite over adjacent is the ratio that we're going to use. Our next step is to start substituting some of the values that we do know. So we don't know the angle, we're going to find that out, so we'll leave that as theta. Now on the top of the fraction we know the opposite side length, that's 10, and then we know the adjacent side length, that's 12. So at this point we can get our calculator out and we can apply inverse tan to both sides and see what we get. So these two will cancel each other out. Then we would have inverse tan of 10 over 12. So my calculator is showing 39.8056. So that means that the angle of elevation is 39 point, now I'm going to round this to 2 decimal places, 81 degrees. Now because we know they both have to be the same, the angle of depression up the top is also 39.81 degrees. Now here we have a really bad drawing of a submarine just below the surface of the water. And this really poorly drawn submarine has a camera attached that can be used to have a look at different objects on the seabed. Now there's a sea star down at the bottom, so that the crew inside the submarine position the camera so it's pointing down, and their system says that the camera is pointing down at an angle of 45 degrees. So they know that the angle of depression is 45 degrees. They also know that the camera and the rest of the ship, but the camera in particular, is 70 meters away from the seabed floor. Now, how far away is the ship horizontally? That means going this way. How far away is the ship from that sea star? Well, we can use trig to answer this question. Now, let's think about some different parts of this situation. We know that this is a right angle triangle, and so is this one. So we've put some little right angle symbols here. Now, this angle here is 45. This entire section here has to be 90 degrees. So we can say, all right, so if the whole section is 90, let's minus 45 to see what this angle is. That also leaves us with 45. So we know that this angle here is 45 degrees as well. And we want to know how far away is it horizontally. So with this triangle down the bottom, we have one side length, we have an angle, and we have another side length that we want to find out and calculate. So let's go ahead and label these side lengths hypotenuse, opposite, adjacent, so that we can figure out what trig ratio is best for this situation. So starting from the angle, we have a side length that's opposite that we want to find out. So we'll label this one the opposite side. We also have a side length that's directly next to the angle. We label this one adjacent because it's a fancy word for next to. So now we have enough info to choose a trig ratio that's appropriate. So here are our three ratios that we can choose from, and we're looking for one that involves the adjacent side and the opposite side. So for this situation, we are going to use the tangent ratio. So our first step is to substitute the values in that we know. So we know one of the angles, that's 45 degrees. Now on the top of the fraction we need the opposite side length. We don't know that. Let's call that x for now. And on the bottom of the fraction we need the adjacent side length. That's 70 meters. So we filled in all of the spots. There's only one unknown in this particular equation, so we can solve for x. If we can get x by itself, that will tell us how long the opposite side length is. So our first step is to try and get x by itself. Let's multiply both sides by 70 because that's the opposite operation of dividing by 70. So they'll cancel each other out. On this side, we'll be left with x. On this side, we'll be left with 70 times tan 45. Great. So at this point, I'd get my calculator out and I'd type in 70 multiplied by tan 45. And my calculator gives me 113.3843. Now I'd like to round this one off to one decimal place. So that's just this one here. I need to look at the number that comes next, which is an 8. It's higher than 5. So this one rounds up to 113.4 meters to one decimal place. So that means that our submarine camera is 113.4 meters away horizontally. So that means this way. 113.4 meters horizontally away from that sea star.